What if I told you there's a fungus that can turn dust into gold? Not metaphorically, not in fairy tales or myths, but literally, biologically, chemically, physically, turn dust into solid gold. It sounds impossible, like some hidden alchemy of nature we were never meant to see. And yet, it's happening, quietly, beneath our feet. The story begins not in a high-tech lab or a billionaire's mine, but in the soil, somewhere in a patch of earth, enriched with decay and microbial life. Researchers discovered something strange: tiny gold particles forming around colonies of a common fungus. The organism was Aspergillus niger, a fungus better known for industrial applications like enzyme production and citric acid fermentation. But in this story, Aspergillus niger plays a different role. It transforms gold ions into solid gold. When scientists first observed this phenomenon, they thought it must be a fluke. But again and again, the results repeated. When gold chloride was introduced to a culture of Aspergillus niger, something astonishing happened. The ionic gold, dissolved and invisible, was transformed into metallic gold particles. Actual gold, tiny, pure, and growing. But how does a fungus, a microscopic filamentous being, accomplish what once seemed like sorcery? The secret lies in chemistry. In nature, gold doesn't usually appear in nuggets or coins. It exists in trace amounts, often bound in rock, or dissolved in water in the form of chloroauric complexes, molecules like tetrachloroauric acid. Where gold exists in the AU3, these ions are rare and toxic to most organisms, but Aspergillus niger transforms them. When exposed to gold ions, Aspergillus niger activates its biochemical defense systems. It secretes a suite of enzymes and reducing agents, organic molecules like glutathione, NADH, and hydroquinones. These molecules act as electron donors, capable of reducing AU3+ to elemental gold. AU0. It's a redox reaction, basic chemistry, yet profound in its consequences. This reaction converts dissolved gold ions into solid metallic gold. But the story doesn't stop there. Once gold atoms are reduced, they begin to aggregate. First, as nanoparticles on the cell wall of the fungus. These nanoclusters can grow, layer by layer, into visible deposits, gold, forming at room temperature, without pressure or fire, just enzymes and time. But why does Aspergillus niger do this? What evolutionary advantage could this strange biochemistry offer? One idea is detoxification. Gold ions are harmful, reactive and damaging to cellular proteins. By converting them into inert metallic gold, the fungus protects itself. Another theory suggests a protective layer. The accumulated gold nanoparticles may form a shield over the fungal hyphae, possibly providing defense against UV light, oxidative stress, or hostile microbes. There may even be electron transfer benefits, where the gold enhances fungal metabolism in challenging environments. Regardless of the reason, the effect is real. Aspergillus niger, through its biochemical machinery, can turn trace gold from the environment into solid, elemental metal. So can humans use this natural process? The answer is yes, and it's called biomining. This emerging field explores how microbes, especially fungi and bacteria, can recover valuable metals from ores, waste, and contaminated soils. While bacteria like Acidithiobacillus are already used to extract copper and uranium, fungi like Aspergillus niger bring new advantages. They grow rapidly, tolerate acidic conditions, and produce nanoparticles with remarkable properties. Gold nanoparticles created by Aspergillus niger are uniform, stable, and biocompatible. These qualities make them invaluable in high-tech applications: medical imaging, cancer therapy, biosensors, and flexible electronics. And unlike traditional methods of gold synthesis, which require heat, pressure, or toxic solvents, fungal biosynthesis is clean. It happens at room temperature, in water-based media, using renewable biomass. It's chemistry guided by life. Imagine the implications. Old mining waste, too poor for traditional extraction, could be colonized by Aspergillus niger to reclaim the last bits of gold. E-waste, from discarded phones and computers, could be processed and exposed to fungal cultures. Over time, the fungus would grow, convert the ionic gold into solid particles, and trap them within its matrix. The gold could then be harvested, filtered, or melted down. No mercury, no cyanide, no smog-belching furnaces. Just biology doing what it does best. And the process is scalable. Scientists are already working on bioreactors where fungal cultures are fed liquid waste streams containing metals. The gold accumulates inside or around the fungal biomass. With genetic engineering, the process can be optimized, boosting reductase enzymes, controlling particle size, and increasing tolerance to higher metal concentrations. But there are challenges. Gold concentrations in waste are low. Recovery takes time, and maintaining sterile, efficient growth conditions on an industrial scale requires infrastructure. Still, the benefits are compelling. Low energy input, minimal toxicity, high value output. It's the kind of process the future demands. What's more, this process shifts our understanding of mining itself. For centuries, we've thought of gold as something to be dug, ripped from rock with explosives and chemicals. But maybe the real gold rush of the 21st century lies in growing it, not underground, but in biolabs, not with drills, but with spores. Fungi, like Aspergillus niger, remind us that the natural world is already doing what we thought only technology could achieve. They are chemists, engineers, even nanotechnologists. In their quiet, ancient metabolism lies a blueprint for sustainable metal recovery, one that could revolutionize how we treat waste, how we think about mining, and how we define value. A speck of gold, formed by a fungus, may seem small, but scaled up, replicated, and refined, it could change entire economies. It could make urban mining profitable. It could make electronics recycling cleaner. It could give developing countries new tools for resource recovery. It could give the earth a break. The fungus that turns dust into gold isn't a miracle. It's a consequence of evolution, chemistry, and survival. It's a product of millions of years of adaptation in microscopic worlds. And it's only the beginning. Somewhere right now, in a forgotten petri dish, or a wet patch of soil, Aspergillus niger is still at work, transforming toxicity into treasure, quietly, efficiently, atom by atom. No magic, no myths, just the science of life.